we have derived two expressions, once for the energy conservation where B t is a defined parameter given by and then we got another expression for from the mass conservation at the surface. Okay. Now, these two were derived for the two different conservation expressions, but if you see that if alpha g is equal to d f and B t is equal to B f, then these two differential equations will be identical. Okay. So, essentially that will get us to solve only one equation with one set of boundary conditions to solve for both the species as well as energy or temperature and species. So, the governing equations then get transformed to and now here we are talking about pure vaporization. So, only species is the fuel species. So, therefore, the species conservation equation becomes just one expression here. Okay. Where this term here equal to this is from overall mass continuity. Now, as we go to the far field and r tends to infinity, then B t tends to B t infinity and B f tends to B f infinity, and at the surface r equal to r s, this is a B t equal to B s surface and B f equal to B f surface, but these are still unknowns. So, we need to solve for this to get the proper boundary conditions. So, what we have is we have a second order differential equation and 3 boundary conditions so far. So, there is a solution for only a particular value of this mass flux. The solution will exist only for a particular value of the mass flux. So, let us go back to this expression now. Let us try to get the solution. So, this is the expression that we are trying to solve. So, let us assume that C g is a constant, a specific heat or the heat capacity of gas is constant, then K j is constant. This too will imply that d f rho g is a constant or alpha g rho g is a constant. This is from standard identities. So, I am just writing there. So, if I integrate this expression once, if I integrate it one time, then we get rho g alpha g r square d b t d r minus equal to a constant. So, just integrating it once. So, let us say the value of this constant is capital A. Now, we can evaluate the value of this constant A by putting the boundary conditions. So, let us put the boundary condition at the surface. So, at the surface, the mass flux of the droplet is given by that we have already derived. Here, assume, we will solve this later, assume that we know the value of this value, assume that this is a known value. Therefore, A is equal to, sorry, just a second. Okay, you can just put R equal to R s in this expression, you can solve for it, you will get this, the value of A. So, if I now substitute in this expression the value of A, we will, I will just change this equation. So, essentially this we got an expression for A by putting R equal to R s and all other conditions, we got this which we are going to put in this equation. So, we get rho g alpha g r square d b t d r minus okay. Therefore, BTS. So, this is at any location is at the surface. Now, we can separate the variables BT and R. So, separating the variables, we will get okay. So, I just separated the variable. Now, let us integrate this. A constant B. Okay. Now, we have to estimate the value of this constant. One constant we have estimated by putting the conditions at the surface. The other boundary that we have is the far field. So, now we put the far field condition to estimate the value of this surface at this surface. So, at this constant, sorry. So, we put boundary condition as at infinity. So, as r tends to infinity, B t tends to B t infinity. Therefore, ln okay. So, the r tends to infinity, this term goes to 0, this becomes B t infinity. So, the constant is this or B rather. Therefore, the solution of this expression now, imposing both the boundary conditions. We have already imposed once the boundary condition at the surface, now putting that at the infinity. The final solution is ln 1 plus B t minus B t s upon Now, this is at any location. If I take this at the surface of the droplet, I will get ln. So, at the surface this becomes equal to BTS, this will cancel off. So, ln 1 upon 1 plus BT infinity minus BTS equal to rho g alpha g. This at the surface R is equal to Rs. So, therefore, finally, we get the evaporation rate at the surface in terms of all the known parameters, which is rho g alpha g by Rs ln 1 plus I will write as capital B T, where capital B is okay. So, now only thing is that we have to evaluate this. If we can get the value of B T at the surface, we can have the full solution. So, similarly, so this now by the way we solve for the heat flux, same thing we can do for the mass flux, right, because by the way solution of this will give B T, which is giving the temperature, surface temperature. Surface temperatures are unknown. So, this the solution of this will give the surface temperature. We also need to know the concentration or the species evaporated. So, for that let us look at the mass this thing, the mass conservation expression. We look at the analogous solution. As we recall that we had very similar expression for the mass flux. So, boundary conditions were same. So, we are just putting that, we do not have to solve it again. Okay. Now, if we assume alpha g is equal to df, then which essentially means Lewis number is equal to 1, because Lewis number is defined as df by alpha g. Okay. So, Lewis number is equal to 1, then from this assumption so, if we assume Lewis number equal to 1, then if you look back at the expression for B T and B F, they become identical. So, therefore, for Lewis number equal to 1, B T is equal to B F, which is equal to B. This is called mass transfer driving force, also called Spaulding's mass transfer number. Okay, is also called Spaulding's mass transfer number. So, with this then we get B T is equal to, this expression we have already obtained earlier. This is the value of B T, right, and this is equal to B F, which is equal to all right. So, this expression gives a relation for this. Here the unknown in this part of the expression, the unknown is surface temperature, that is still an unknown. For this part, surface concentration or mass fraction is the unknown. Okay. because this is something is the pure fluid inside that is known, this is far field that is known, at the surface what is happening, these two are unknown. So, this expression gives a relationship between, if we solve by solving this, if we get a value of B t, we get the surface temperature and the concentration. Now, if we get one more relationship, then this equation can be solved. We still do not have, because as you see in this equations, this remains an unknown, that T s remains an unknown. So, we have to get one more equation to solve this, because unless we know this value, we cannot solve for B t anyway. So, we need one more equation, and that comes from phase equilibrium. What it says is that the liquid and vapor phase are at equilibrium. So, for that, then we use Clausius-Clapeyron equation. It says that this is the Clausius-Clapeyron equation. This is the vapor pressure, heat of vaporization by R, and this is in terms of latent heat of vaporization and R v, where R is the molecular gas constant divided by molecular weight of the vapor. Now, we know that heat of latent heat of vaporization is a constant, right. Typically, for a particular fluid at a particular pressure, latent heat of vaporization is constant, and there is latent heat of vaporization. For example, if I look at water, it evaporates at 1 atmosphere pressure at 100 degrees Celsius. We have been discussing so far all the processes independent of pressure, right. So, if we consider that this process also to be independent of pressure, then latent heat of vaporization does not depend on what temperature you are in, because it will happen only at a fixed temperature. So, that heat is independent of temperature as well. So, therefore, is a independent of pressure and temperature. So, L is independent of pressure and temperature. If that is the case, then we can integrate this equation very easily, because this becomes a constant. So, when this is a constant, we can integrate this equation and we get an expression for vapor pressure as okay. Now, at the surface, if I look at the surface, the temperature is T s, the vapor pressure is P s for the vapor. So, okay. And this is nothing but mole fraction times the pressure okay. Therefore, Y f s now, we have one equation here, these two are equal, right. In this two, we have these two unknowns, because we have shown that these two are equal from the solution. So, this two, we have two unknowns here, one equation. Now, we have got another equation here relating this and this. So, everything here is also known. this is the molecular weight of fuel, this is average molecular weight, a particular species average molecular weight, this is the pressure which is known, this is a constant coming from that expression which can be very easily estimated. So, heat of vaporization is known. So, everything here is known except YFS and TS. Here also I have TS and YFS as the unknown. So, we have two equations, two unknown. So, now this can be solved. But the beauty of this is we do not have to solve any differential equation, both of these are algebraic equations. So, with the assumptions that we have made and the process that we have followed, we have eliminated differential equation, we have now just to solve two algebraic equations. So, let us see how we will solve it. I will give a solution which is a graphical solution. Okay. So, let us say if I plot right surface temperature let me call this equation A, let me call this equation B. Okay. Looking at equation A, if I choose a value of Ts in this equation, right, let us assume a value of Ts, then we can solve for YFS in this equation. So, we can get a curve of this. So, when Ts is equal to the T naught, okay, when Ts is equal to T naught, we get this is equal to 1. All right. So, it starts from 1 and then as we come towards the surface, as Ts value starts to deviate from the internal temperature, there will be evaporation and the concentration is coming in. So, this is the plot of equation A, and here you can see is an exponential expression. So, this is the plot of equation B. So, here also we can choose a value of Ts, we can get YFS and we can plot this. We see that this is the point where these two solutions are intersecting. Therefore, this is the point we have the simultaneous solution for both these equations. So, therefore, this value here is my Ts and this is YFS, right value, right. So, this is the Ts value, this is the YFS value, and this point here where it starts to exponentially increase, that is the boiling point. Actually, sorry, boiling point will be somewhere here. This is the boiling point where all the vapor at the surface, everything is only vapor. Okay. So, that is the boiling point.
So, boiling point is beyond YFS equal to 1?
At YFS equal to 1.
Oh, okay.
I just wanted to show that here. So, YFS equal to 1, this entire vapor has come out. So, after that is a pure surface, pure fluid, pure fuel vapor rather. So, this is the TB is the boiling temperature. So, essentially what we see from this is the surface temperature is below the boiling point for the burning liquid, okay, because if it reaches the boiling point is immediate complete evaporation. Okay. So, surface temperature is slightly below the boiling point of the evaporating liquid, and however, if this is pure vaporization, but when it happens in the combusting environment, typically the ambient temperature T infinity is very high. In that case, Ts will be almost equal to boiling point. Okay. So, if the ambient or around temperature around the droplet is much larger than the initial temperature of the droplet, then surface temperature will reach the boiling point value. Okay. So, if all right. So, in that case B is equal to all right. However, if T infinity is less than T b, that is you have a heated liquid in a low temperature environment, then also evaporation takes place, like if you take water in a container and boil it, right. So, there the liquid is a higher temperature than the ambient. So, same that possible, that is also possible. So, in that case surface tension temperature will be almost equal to the outside temperature. So, for that scenario in practical conditions where we see this ignition, right. Unless we have ignition, we will not have the high temperature. So, a cold liquid is coming in, which is because of the pump at slightly higher temperature than the engine. So, there we have this condition, okay. And from this we can estimate how much more energy is required to take it to boiling, okay. How much more energy is required to take it to boiling and evaporation. So, the ignition energy can be estimated from there. Now, so this is again pure evaporation, that we have a environment which is either hot or cold, pure evaporation is taking place. Next step, most logical step is, what if after evaporation we have combustion. So, we have already done the formulation, but now we are going for practical solutions. So, this solution does not involve any combustion part, just the evaporation part. Next, let us talk about evaporation followed by combustion. We have fuel is vaporizing. All right. On this side, we have oxidizer, which is oxygen, and neutral species like nitrogen. Okay. So, outside the fuel vapor, we have oxygen and nitrogen. Then, now since the reaction is taking place, we have the product species as well. Okay. So, let us say all the product species I am representing by P. So, essentially here in the fuel we have species F representing the fuel, oxidizer and neutral elements represented by O, which is the oxidizer, and product P. So, this is where the product is happening. Okay. So, symbolically then we can write that this is what is happening: exothermic reaction, F plus O giving products plus heat, and then we can have reaction mechanisms, etc. We will not go into the details of that. So, let us say that my chemical reaction I will write as, so this is a simple chemically reacting system. So, if we say that I have F gram of fuel and 1 gram of oxidizer, then I will have 1 plus F gram of product, right, and how much heat? If I am burning F gram of fuel and my heating value is H, then heat is F H, right, where H is the heating value, then or calorific value of the fuel. So, this is the amount of heat that is produced. So, that is the chemical reaction. Then now, since chemical reaction is happening, we will have the reaction rate, right, the specific reaction rate. This is given by K F that is coming from Arrhenius law. Okay. Here rho f and rho naught are density or mass concentration of fuel and oxidizer. K f is the exponential exponential factor, E is the activation energy. So, from this then the volumetric rate of production of fuel, or the not production, rather the change, volumetric change in the rate of fuel. Here fuel gets consumed, so it will reduce, right. So, this is equal to minus F and the reaction F time reaction rate, right. Similarly, we had 1 gram of oxidizer. So, the rate of change of concentration or the mass of oxidizer, since we had 1 gram, 1 times oxidizer also gets consumed. So, fuel and oxidizer getting consumed, that is why you have negative sign. However, the heat volumetric heat addition because of chemical reaction is equal to F H W dot omega dot, right. This is the volumetric rate of reaction, the amount of fuel and heating value. Then you get a very simple reaction equation. Okay. So, you get 3 very simple reaction equations. It is just writing this again and again. Now, let us make some assumptions, because we will be solving the same problem with reaction happening. So, for that we need to make some assumptions. Assume that the diffusivity coefficient for oxidizer and the fuel are same. Okay. That we can assume if both this fuel have after vaporization have almost equal density, then we can assume that. Typically, most of the hydrocarbons and oxygen have after evaporation almost same density. So, it is a fairly good assumption. However, if you are using hydrogen, then there is an order of magnitude difference in diffusivity. So, that this equation assumption may not be valid there, but for most practical hydrocarbons this is valid. So, we can say that this is equal to D. Then another assumption we make is that thermal diffusivity is equal to molecular diffusivity, okay, which essentially means Lewis number equal to 1. This we have already assumed for the vaporization case, we assume the same thing here, and we assume that C g, K g, rho g, D equal to are all constants independent of temperature and composition as well. Okay. Temperature and independent of temperature constant and composition also. So, essentially they are function only of, if they are independent of both temperature and composition, there will be independence of R or the spatial, there is no spatial variation. So, these are constants, we assume these three. With this, then now let us go back to the conservation equations and solve them. So, first is overall mass conservation. This says m dot equal to rho g stands for the gas phase. This is equal to all right, where this is the mass rate of mass, but the rate of mass variation, this is the mass flux. Now, we have already discussed this before, so I just write this surface mass flux plus at any other location. Okay, so, it is radially spreading. So, at any radial location we can estimate. Now, coming to the energy conservation. In the previous case, when there was pure evaporation, this was equal to 0, right. But now, we have heat added because of chemical reaction. So, this term will come in. This term was not there in the pure vaporization case. Okay. So, this will imply Kg can be written as rho g alpha g Cg okay. Since Cg we have assumed to be constant, so it can be taken inside the differential term. All right. So, you get one equation here. Let me call this equation 1. Similarly, for the mass conservation, we can get species mass conservation, we can get another expression, which is, let us do it for the oxidizer first, because species, remember that every species now will have a different equation. So, for oxidizer we have rho g d d d r r square okay. This is the conservation of oxidizer. Now, similarly, we will have conservation equation for fuel. This will be equal to once again rho g d d d r okay. Then let us look at this expression. This can be simplified as using the assumptions that we had already made. Now, this H is the heating value. So, that is a constant, right. So, we can multiply each term here in the inside the differential term by H. Okay. So, that is what I have done, just multiplied H by this term, all these terms in the equation. Now, let me call this equation 2. If I now add equation 1 and 2, okay. So, adding equation 1 and 2, you will get too much of mathematics, this board. Okay. Now, what is happening when we add this 2, this is equal to 0, we have already proved, right. This and this plus this is equal to 0, we have already proved. So, therefore, this term, when we add this term goes away, we are left with only this. Now, similar to what we have done previously, we define a new variable. So, let us define a new variable now, B f t. Earlier we defined B t, which was for temperature separately, B f which was for concentration separately. But now, if you look at this equation, both are together, it is a combined equation. So, we define a parameter which is given by okay. With this now, after defining this, if I put this back into this equation, we get our simplified expression. Right. So, these equations have now simplified to a relatively simpler expression. Now, let us look at the solution. From the boundary condition at the surface, then we can integrate this equation once, and put the condition at the surface. Okay. Similarly, this is from the boundary, this is a boundary condition for the heat flux. Similarly, for the boundary condition for the mass flux, we can get another expression. At the surface into H. Okay. then okay. So, combining this two we get this expression. Now, if I look at this term here, this is nothing but BFT. So, therefore, this is equal to rho g alpha g d dr of BFT, as we have defined here BFT to be equal to this. Now, let us bring in the boundary conditions. So, at r equal to R s, BFTS, at r equal to R infinity, it is BFT infinity. Okay. We can define, we have to define actually some more expressions, because again we are discussing a reacting case. So, we should have some variable representing the oxidizer and some variable representing the fuel. So, we will define a parameter BOT representing the oxidizer. This is equal to this. Again, these are defined properties. Similarly, for the fuel, we can define the BF naught okay. Now, all effect of this is essentially, if you look at these variables BF naught, BFT, BOT, these are all essentially variable representing certain parameters. They represent temperature and species concentration. So, we can consider them as a generic variable B, let us say. Let us say we have a generic variable B representing all three, okay, depending on what we want to put, we can put. These are the generic variable. These variables are called Zeldovich variable. Okay. So, in terms of this variable, now if I go back to these equations, I can get one equation in terms of B representing the variation in all other species, all other parameters. So, that in terms of the Zeldovich variable, my differential equation will be, because here if I otherwise I have to solve each of them separately, we have to solve for temperature separately, concentration of oxidizer separately, concentration of fuel separately. So, we just write in terms of one variable B. So, in terms of that variable, this will be okay, where this B here is any one of the three. Then at the surface, okay, now any variable we satisfy the above equation with the same type of boundary condition is called a conserved variable, right. So, any variable B, as long as it satisfies this equation with similar boundary condition, is called as conserved variable, very similar to conserved scalar approach that is used for solving combustion problems. So, solution of that will lead to, I am not going to a detailed solution, solution of that will lead to, solution method is very similar to what we had discussed earlier, that is why I am not going into that, I am just integrating this. Okay. So, once again this B is our Spaulding's mass transfer number. Earlier we have done it for a pure vaporization case without combustion. Now, this will be with combustion. So, the form of this will be slightly different. I will write that. Okay. Now, what is the difference between what we had before and this one? Previously, since it was pure vaporization, we did not have the reaction term. So, this term was not there, this term was not there. But now, because of the reaction, heat of reaction is also appearing along with the concentration of fuel, because this term essentially represents how much heat is being generated by the chemical reaction, which is taking part in the heat transfer part. Okay. So, this is the expression now with the reaction. Now, in this I would like to point out one more thing. When we have this expression, we have already introduced these two conditions. That far field away from the droplet, there is no fuel vapor. So, the mass fraction of fuel vapor far field away is 0. Inside the droplet, there is no oxidizer. So, YF inside the droplet represented by 0 is equal to 1. This is purely pure fuel. Okay. And at the surface, we have the mixture. So, these two are already incorporated in this expression. Now, with this then, this is one of the variable, we will have two more variable. One is BFT. Similarly, we can have another B which is equal to BOT. Okay. And we can also have BFO. Okay. So, by equating these equations, since all of them have the same value B, so by equating these equations, now we can solve the problem. So, but again, so essentially our two unknowns are Ts and YFS now. So, we have to solve for this. Equating this will give us one equation. Once again, we need one more equation to close the problem, and that equation will come from phase equilibrium Clausius-Clapeyron equation. So, same process we will be following. So, equating any two of this gives me one algebraic equation relating Ts and YFS. So, I get one equation from there, other is the Clausius-Clapeyron equation. So, again we will go for a graphical solution. So, once again I will draw the graph. So, the graphical solution will look like this. The boiling point, surface temperature Ts, YFS, Ts, Tb. Okay. Now, in this case, since we are talking with combustion, so in this case flame temperature is always much greater than the boiling temperature. Therefore, typically Ts is almost equal to Tb. unlike in previous case where we had two possibilities, but here is always used to be going to be equal to this. So, we define this parameter then this parameter B is a thermodynamic property of a liquid fuel. What it represents is H is the heating value, F is the stoichiometric fuel requirement. So, for if you have to burn 1 gram of oxidizer, the amount of fuel requirement for that in the stoichiometric condition, that is F. This is the concentration of fuel in the far oxidizer in the far field. So, essentially the ambient concentration. This is the far field temperature. This is the specific heat or the calorific value for the gas, not calorific value, the specific heat for the gas or the heat capacity for the gas. This is the boiling temperature. Infinite the ambient temperature, boiling temperature, latent heat of vaporization, then heat capacity for the liquid, again boiling temperature and liquid temperature. So, as you can see that this is all function of the liquid properties. So, is a thermodynamic property. Once we, so now with all these actually what we see is that actually we do not need to solve for anything. We have a very simple expression. We have gone through all the detail, we got a very simple equation. This equation will tell us what will be the value of B. Once we have this value of B, we can put it in the expression we get the mass flux. Okay. So, this value of B we can calculate without having to solve for anything. It is a thermodynamic property. Once we have this, we can put in this equation, we can solve what is the mass flux. Okay. And then what we see here from this expression, that this is inversely proportional to the surface radius. So, essentially what it shows is that as the droplet size decreases, the burning rate increases. Okay. Now, after going through all this, we have shown this, but at the beginning of our discussion, I had given some empirical expressions. Which was m dot is equal to some constant times the droplet diameter radius, and we had got the d square law. Okay. These two at the beginning I have discussed. Now, let us put them together. We have also shown that m dot is equal to 4 phi r square r s square times double dot mass flux. Now, this mass flux let us take from what we have derived there. Okay. Therefore, comparing these two, we get an expression now for k prime. Okay. So, once again we see that knowing the fuel properties, we can get this constant k prime. Then we can directly plug into that expression and find out at what rate the evaporation is taking place. Okay. So, we have gone through lot of derivations and solutions, but final solution is very simple, because we have converted everything to some algebraic equations, and that was possible to do because we had self similar solutions or self similar expressions. So, this gives us the value of this constant k prime. We still have to do another constant which is, let us come back to this equation. Now, from the solution that we had for the MS, we had an expression for dr dt, right. So, this dr dt is equal to nothing but right, because d is equal to 2r. So, it is half d dt. So, dr dt is half d dt, and this solution we have already obtained the expression. Because m dot s was in terms of dr dt, right. So, we can get this expression here. We got this, go back to the d square law. Okay. So, from there okay. Putting it back into this, you get k equal to so the constant for the d square law also can be obtained in terms of all the fuel parameters. We do not have to solve anything. By knowing the fuel that we are using and oxidizer we are using, we can directly get this expression. Once we have this, we have at the beginning showed that the evaporation time is given by this, right. So, now we put it here, we will get one expression. Right. So, you see again as a fairly simple solution. Okay, so now let me summarize what we have discussed so far. Okay, that I will just stop with that, because we have gone through a lot of mathematical derivation. Actually, we did not solve anything. What we did was, with those mathematical derivations, we just converted them to similar equations. Then we say that they will give same solution if the boundary conditions are same, and then we just equated the boundary conditions to get the solution, nothing else. So, now let us summarize whatever we have discussed. So, first of all, the vaporization mass flux, we have proved that this is equal to rho g alpha g by R s ln 1 plus b. If you look at the pure vaporization part, it was only ln 1 plus b. So, this term here, which is a constant, is coming because of the heat transfer effect. Then next what we have shown is the mass flux, mass transfer number when we have chemical reaction going on is given by now. This value can be estimated from thermodynamic tables. This is because it is thermodynamic quantity. So, can be given deduced for any given situation without any difficulty by just using any chemical engineering table. Okay. Then we have proved that the evaporation constant for d square law is equal to Once again this can be estimated without any difficulty by just knowing the type of fuel that we are using. We have also proved that the burning time of a droplet is given by this. Now, the evaporation, first let us go to this expression, the evaporation rate from the droplet. So, this evaporation rate depends on this product rho g alpha g, and rho g alpha g is equal to nothing but so it depends on the conduction coefficient and the heat capacity of the gas. Okay. Then next it depends on the size of the droplet R s. So, this has a strong influence. So, the atom after that is why we have to go for atomization, fine atomization, because if the size is large, as you can see that the evaporation rate is going to be very, very small. So, it will be burning at a much lower rate compared to what we want. Then it depends on this parameter B, which depends on the fluid properties. Now, here from this equation what we can see from this equation, as B increases m dot s increases, and increase m dot s is what we want, because we want it to evaporate faster. The faster it evaporates, the smaller combustion volume is required. So, that can be achieved by increasing this value of B. So, just summarize that what can we do to increase this value of B. So, what we see is that as B increases, m dot s double dot increases. So, we have faster evaporation as B increases. Now, how do we do that? We can have large value of H, right. We can have higher value of H, that is the higher calorific value of the fuel. So, that is why particularly for aircraft application, now if MS is low, it will take longer to evaporate and burn, right. Now, that means you need a longer combustor. For aircraft application, the combustor size has to be minimized. That is why for power generation on ground or for gasoline engines, all over the world people are diluting the fuels with alcohol and burning it. Alcohol has a much lower heating value compared to aviation turbine fuel. So, even though we know that the combustion characteristics will be good, for aircraft application we do not burn with alcohol, because the combustion rate will be so slow that you will require much longer combustor, which will increase the weight. Okay. So, you can see from here we need to have large heating value, alcohol has a lower heating value compared to the fuels. Next, what we need is large Y naught infinity. Okay. Now, let us see that for most other applications, let us say for aircraft application, for application in power plant, for application in other transportations, this value is fixed, because we have air all around. So, we say that we cannot do anything about it, but rocket combustors are much smaller compared to other conventional combustors. They produce much higher energy, because rockets they carry their own oxidizer, they do not have any other dilutant. So, it is a pure oxidizer concentration. Therefore, Y naught infinity is 1 for rockets, but for everything else, because it is air, 78% is nitrogen. So, the oxidizer concentration is low. That is why rocket has a much better efficiency, with a much smaller size we can get much higher power. Next, we should have L as small as possible. Now, this is something that unfortunately these two contradict each other. high H and low L. So, therefore, it is not possible to always meet it. So, ideally if you have a hydrocarbon which can evaporate at a lower energy, we should get better combustion, better ignition, better evaporation rate. Now, this is being used, this concept is being used now progressively, actually not being used, but it will come very soon in automobiles, particularly diesel engines. If you look at the evaporation rate, diesel has a much higher evaporation rate compared to lighter hydrocarbon like heptane and all. Okay. So, now people are talking about supercritical combustion, a supercritical atomization, where the fuel is like diesel is mixed with certain amount of lighter hydrocarbon. So, therefore, the overall value of L reduces, we get better efficiency, better combustion efficiency, better lower emissions. So, that is essentially mixing different type of fuel together, so that we get the higher heating value for heavier hydrocarbon, lighter hydrocarbon gives us this advantage. So, essentially both of them we can bring together and get better combustion. So, now this is, as I said, is being tried out particularly in Japan and Korea, they are big time investing into this. So, maybe in 5-10 years that will be the fuel technology, where they are mixing diesel with decane, heptane, and octane. So, that is going to, particularly for the diesel cars, that is going to have much better combustion. Then what else we can do? We can have T infinity greater than T b, that is always the case anyway, and particularly for most of the applications in particular the gas turbine applications, because the air comes through the compressor is already heated. So, we always have T infinity greater than T b anyway. So, that helps in auto ignition also, and then T naught almost equal to T b. So, if you preheat the fuel, we get much faster evaporation and burning. So, this is another. So, these are the conditions that we can have to get better combustion from liquid fuel. Now, wide variation in B would lead to only small changes in MS. This is another important thing. The variation in B, because the dependence is logarithmic, okay, 1 plus B. So, if I look at okay. So, very large variation in B will bring fairly small change in m dot s. Okay. So, for a very large, let us say if I take one parameter, let us say R s, okay. What we are seeing is that if R s is small, m dot s is small, but B will compensate for that impact. Okay. So, for a large variation in B, for a wide range of fuel, let me put it this way, for a wide range of fuel, the value of MS is not going to change much, as long as we are within certain range, and that is the advantage, that is why we do not have to separately study all type of fuels. We can do one surrogate test and that is good enough, as long as we are in the ballpark of certain parameters. So, with this let me just give you some of the numbers to just give and get an idea of what happens in this case. So, for different fuels I will give the value of B. So, if you have N pentane, the boiling temperature is about in degree Celsius is about 36. The value of B is 8.15. We go to N octane, it is 125, but the B is 5.24. So, you see that this variation in B will have very minimal impact on m dot s, because it is ln 1 plus B. So, it will have very small impact on m dot s. You go to gasoline, boiling temperature is 155, but B is 4.98. Kerosene 250, this is 3.86. Light diesel again 250, same boiling point, 3.96. Medium diesel 260, this is 3.94. Heavy diesel 270, 3.91. Toluene xylene 130, 5.76. So, essentially what you see is that the influence of boiling point is much more on B, right. Where the boiling point is far off, we get is lower, we get a quite high value of B, but when boiling point is high in the diesels, its value is low, and if boiling point remains same, B also remains same almost. So, there is a quite strong dependence on boiling point. Secondly, however, if I look at this B, it is not varying much. So, m dot s will not have much of impact. So, if I have to look at then the what will influence it most is R s, the size of the droplet, because that will have a direct inverse relationship, that m dot s is 1 by R s. So, if you go for a larger droplet, it will evaporate much smaller compared to a smaller droplet. So, therefore, the fuel composition and all does not have much of impact. And another thing, that since we are seeing that the B is not varying much, so essentially then it becomes essentially function of droplet size. B is depends on the fuel property. So, if there is no dependence or much dependence on that, we do not have to test it with the real fuel. We can test it with water, right. We can test it atomizers with water, and then we can infer from that the droplet size we are measuring, we can infer for that what will be the impact on combustion, right. So, that is a huge advantage, because doing a test with the actual fuel is very dangerous and expensive, because we are creating fuel vapor, it may catch fire, particularly since most of the measurement instruments are laser based, right. So, laser will create hot spots, it may catch fire. So, therefore, nobody would like to do combustion spray measurements with actual fuel. We can do with water, because the B is not much of a factor, you can just get the R s, and from there we can infer about the emissions and everything. So, that is the advantage of doing this. So, although the process is very complex as it looks like, the solutions are much simpler. Okay. So, therefore, we do not have to bother much about also. And that is the reason that although whatever you studied in the other part of the course is purely gaseous combustion, right. Now, the liquid impact can be very easily brought in into gaseous combustion by this. So, we do not have to have separate, because physically these two are not far off. So, you can understand the physics from the gaseous combustion, and liquid combustion variables can be very easily brought in through this analysis. Although, like I said, initially the equations look much difficult, but the solution is very simple. Okay. So, I will stop here. Have any other question?